Okay, so what we have here is the logarithmic rules. So we're going to have the product rule, the quotient rule, and the power rule. And these will explain how your logs can manipulate to get specific answers for questions that involve logs. So for the first rule, you have the product rule. So you have any log with x times y will expand out to log x plus log to the y. And now if you go down to the quotient rule, you'll have just about the same thing, but instead it's x over y, and you'll end up getting log b to the x minus log b to the y. And what that does is, those show the difference between those two. And then finally you have the power rule, which is this part right here, this exponent on top of the logarithm. What's going to happen is this is actually going to come around to the front, and you're going to have y times log b to the x. And those basically explain the rules of logarithms. Now, getting into some examples, if we want to try and condense equations down into a single logarithm, you can use the log rules you have here, and it'll make it super easy for you to get single logarithms. So you have log b to the 5th plus log b to the 30th minus log b x. So what you're going to end up getting is log b 5 times 30 over x, because if we go back to the product rule, these two, since they're plus, the 5 will multiply by the 30. That's what you get on top. And then you'll get x underneath because it's minus, and that's the quotient rule. So you end up getting 5 times 30 over x, which results in log b to 150 over x. Now you go to example 2. You have log b to the 8th minus 2 log b to the 4th. What you're going to do here is, this part's already as simplified as we can get it. This second term, you're going to take the 2 and you're going to shift it over to the top, so you're going to get log b 4 to the 2nd, and it's still minus, so you're going to take the quotient rule of that, and you're going to end up getting log b 8 over 4 squared, which is 16, and that reduces down to log b to the 1/2. Now if you want to expand logarithms from a condensed form, you can just use the same exact rules in reverse. So for example, you have 4 log b x over y. What you can see here is, obviously you have an exponent in front, so you're going to want to take that over and put it on top of the x over y. And you can see here that you're going to end up using the quotient rule because there's a division inside the log. So you end up getting log b x over y to the 4th, which comes out to log b x to the 4th over log b over y to the 4th, which ends up getting you the answer of log b x to the 4th minus log b y to the 4th.
Okay, so we're going to do exponential functions. There's 2 equations for them. A of t equals a of 0. E to the negative kt is decay rate, because there's a negative k, which is originally a positive constant, but it becomes negative because you're decaying. And then there's a of t equals a of 0, e to the k of t, and that's positive because it's growth rate. And a of 0 demonstrates the original amount that you started with, t is time, and like I said, k is the positive constant. And then just a brief example of the decay rate could be the half-life. This is just like an easier example, so you don't need to use the equation for it. But let's say you have an x element that has a half-life of 4 days. Initially there was 25 kilograms of the element x. How much remains after 12 days? Since it's half-life, that means x is decreasing by half after 4 days. So let's say you started with 24 after 4 days, you take half of that, so you end up with 12. And then after 4 more days, which is a total of 8 days, you multiply by half, which you end up with 6 kilograms. And then after 4 more days, that's 12 days, you multiply by half and you end up with 3 kilograms. So after 12 days, you end up with 3 when you started with 24.
Okay, so the problem we have right here is an exponential decay problem. It reads, there are 70,000 people on an island. A virus has killed 34,160 of the population in 3 weeks. What is the rate of decay? So what we'll be finding is the k constant in the equation a to the t equals a to the 0 e negative k to the times t. So what we want to do is we want to find exactly how much of our population do we actually have after 3 weeks. So what we do is we take how many we've killed off versus the initial amount, and we get the number 35,840. So we can plug that into the equation on the left side, and we'll get the equation 35,840 equals 70,000 e to the negative 3k, because we have 3 weeks and we have a negative k as our decay rate. So what we want to do is we want to get this e all by itself. So we're going to take 70,000 and put it underneath the 35,840. And then from there we can take natural logs of the function to cross this e out. So what we're going to do is we're going to take the natural log of 35,840 over 70,000 and the natural log of e to the negative 3k. This will cross out, leaving you with something like this. The natural log of 35,840 over 70 to the negative equals negative 3k. From there, what you can do is you can take 3k and put the negative 3 under it, and you'll get k equals natural log of 35,840 over 70 all over negative 3. And if you were to compute that with your calculators, you would end up with a value that is k equals negative 0.17.
So right now we're going to be doing the exponential growth rate equation. So a of t equals a of 0, e to the k of t. And a of t is pretty much what we have in that certain time period. A of 0 is the original rate, k is a positive integer, and then t is just time. So we have our problem here. There are 500 blood cells and they double every 5 minutes. How many will there be after 3 hours? So what we're missing from this equation is the k, because we have the original amount, which is 500 blood cells, and we also have the time, which is 5 minutes. So we're missing k, but we know that it doubles every 5 minutes. So even though this says 500 e to the 5k, we know that it doubles, so we'll just double 500, it'll be 1,000. So then we'll just divide by 500 on both sides. We'll just get e to the 5k equals 1,000 divided by 500, and you'll get 2 here, which should happen every time that you double, because 2 will represent the doubling. And then you just take the natural log of e to the 5k and the natural log of 2. The natural log and e will cancel out, and the 5k will come in the front. And then we'll have 5k equals ln of 2, or natural log of 2. And then your k will end up being ln of 2 over 5. And then now that we have k, we can just go back to our problem. What's our problem asking us is how many will there be after 3 hours. Since our hours conflict with our minutes, we're going to convert hours to minutes. And since we know that there's 60 minutes in 1 hour, it's going to be, we're just going to multiply it by 3. So it's going to be 180 minutes in 3 hours. And we're going to add it here. So a of 180, just because if we go back to our problem, that's supposed to be t, which is time, equals 500, original equation, to the e over our k, which is natural log 2, times 5. So we'll do this, and then what we just did is, this is the same as natural log 2 over 5. We just put the 1/5 in front to make it look nicer. Then we times it by t, which is 180 minutes. And then what happens was the 180 and the 5 canceled out, and we ended up with 36. So 500 e to the 36 natural log 2. This ends up being a really big number, and since there's a natural log and there's an e, they cancel out and become 1. So it becomes 500 times 2 to the 36 power blood cells. And that's your answer. That's how many blood cells are going to be after 3 hours if they increase or if they double every 5 minutes.